Hi guys, I hope you're all doing well. Today I want to give you a brief introduction to spaCy, which is a pretty cool library for advanced natural language processing (NLP) in Python. It has state-of-the-art language processing powers basically, and is designed to be industrial grade, though it's also still open source. So it's currently growing into becoming an industry standard library for NLP. And what's quite cool about it is that it combines both rule-based and machine learning approaches. Um, spaCy has a couple of shelf features and many pre-trained models in different languages, predominantly English, but also German, for example, which are just amazing out of the box. And at the same time, spaCy allows you to train your basic custom models on your own data to optimize it for your specific use case. All right, before we start this off, I linked this cheat sheet here for you guys to quickly have all the most important features at hand. As mentioned before, spaCy comes with pre-trained NLP models that can perform most common NLP tasks, such as tokenization, part-of-speech tagging, named entity recognition, lemmatization, transforming to word vectors, etc. The installation is quite straightforward. It can be achieved via the PIP path. On their website, there's also documentation if you use, for example, a Mac or a Linux system. So before we start off with any coding, I think we first need to understand how spaCy's container architecture works. These are spaCy specific objects that contain a large quantity of data about the text itself. On top of that is the NLP object, which basically works like a function to analyze text. So you input the text into this NLP object, and then a variety of text analysis procedures are done by default. The doc object is basically at the core of this whole procedure. So when you process a text with the NLP object, spaCy creates this doc object, short for document. The doc lets you access information about the text in a structured way, and no information is lost. The doc behaves like a normal Python sequence and lets you iterate over its tokens or get a token by its index. Below that are the token objects. So these represent the tokens in a document. For example, this could be a word or a punctuation character. To get a token at a specific position, you can just index it into the doc. And these token objects actually also provide various attributes that let you access more information about the tokens. We will talk about that pretty soon. The span object is a slice of the document consisting of one or more tokens. It's only a view of the doc and doesn't contain any data itself. So to create a span, you can just use Python's slice notation, and these spans take at least 3 arguments. So first the doc itself, the doc it refers to, the start, and the index of the span. As mentioned before, spaCy comes with pre-trained models, and the 3 most important model packages: a small, medium, and a large English model. As I said before, these are pre-trained models that you can easily use. To access these models, you have to load them first, which works like this. To illustrate the first steps with spaCy, I just took the Wikipedia article Data Science and did the first steps with spaCy. Mentioned before, we now use this NLP object on our text, and this produces the doc container. To illustrate the first steps that now happened within this doc document, I first provided a view of how Python would tokenize the text. So Python would just split the words and sentences into its letters, so there's no real identification of words or sentence boundaries or whatever within the doc container. That actually these sentences are perfectly tokenized, so each word is perfectly separated and identified, and also split from other types of parentheses, for example. So even if we did this with the standard Python .split command, we wouldn't come to the same tokenization, to the same splitting. As we can see, for example, the parenthesis is still attached to a few words, so this wasn't really successful. Another cool feature is that spaCy immediately identifies the sentences, so we can access the individual sentences with .sense. As we can see, spaCy was basically able to split this paragraph into its individual sentences. You can access these like this. You could say that tokens are basically at the heart of our NLP procedures. So these are very, very important objects in NLP. And what is quite cool about spaCy is that with its pre-trained models, it can now give these tokens certain attributes which can be accessed via .attribute. So for example, you can access the text of a token. You could, for example, see which words were placed before the specific token. You could access the lemmatized version of the word. You could conduct some of morphological procedures with the word. And you can also, which is very interesting, you can also access the part of speech from this specific token. In code, this could look something like this. So we have the sentence above, it uses techniques and theories, etc. And now we are looking into the 20th token, which carries the text information. So it's here in the line of information science. And now we can look into the different attributes that this token has. So for example, we see its head, its left edge, its right edge, what type of word it is, what language it is, and what dependency link it has. This leads us to so-called part-of-speech tagging, which is a very, very powerful tool provided by these pre-trained models. So as I said before, we basically load these pre-trained models, which help us to make statistical predictions for our context. So with these models, we can basically mine context-specific information. And one of these application fields would be to predict the part-of-speech tags or mine syntactic dependencies or named entity. The prediction of part-of-speech tags is quite straightforward. The idea here is that the statistical model can predict what part of a sentence, so for example, the verb, each token is. The next step is then the prediction of syntactic dependencies. This is basically the prediction of the dependency label, so how these words or tokens are interlinked. This gives us a lot more information as to in which context a specific word or token is occurring. Another application field for these statistical predictions is so-called named entity recognition. Named entities are real-world objects that are assigned a name. So for example, this could be a person, an organization, or a country. spaCy supports a long list of named entities and basically tries to predict these entities in your provided text. The doc.ends property lets you access the named entities predicted by the model. It returns an iterator of span object, so we can print the entity text and the entity label using the label underscore attribute. As an example, I looked up a recently published article in the New York Times about the World Economic Forum. You can use the spaCy render function to show this in a fancy way. So here you can see all the different real-world entities spaCy identified in this text, and we can further work with these entities in our analysis. I prepared another example for this where I combined the named entity recognition and the part-of-speech tagging to extract specific information. So for this, I prepared two texts which contain some financial information. This could be, for example, part of an annual statement. I then iterate over these texts, and I'm looking for the entities money, which contain basically these numerical values. So now with this line, I'm only targeting tokens that have this entity type money. Now I'm looking into the dependency attribute of these tokens, which have the identity type money, which in this case should be or could be the direct object or an attribute. And then I basically look for the tokens that are governing our money token. So in this line, I'm now moving left from the head token of our money token with this command .lefts. We can now go beyond the first dimensional dependency. So if you envision this graph from before where we had these arrows that link the individual tokens together, there's always only a one-dimensional relationship. And with this command .lefts, we can move further in these different arcs of the tree. And then I just want to print the basically subject. So now I want a nominal subject that is basically related to our money token, and this would be the output here. So we can see that we now find the context in which the money entities come up with. We see this number 2.7 million. It has been used in the context of prior year, and that, for example, $12 billion was used in the context of the current revenue. spaSy can also do some semantic similarity analysis, so it can compare two objects and predict how similar they are. For example, document spans or single tokens. The doc token and span objects have a dot similarity method that takes another object and returns a floating point value between 0 and 1, indicating basically how similar they are. One thing that is very important, in order to use similarity, you need a larger spaSy model that has word vectors included. So the small English model doesn't have these vectors. So you can use, for example, the medium or large English model. Here's also documentation of the differences in these pre-trained models. So we talked about the lecture. Similarity is determined by using these word vectors, which are a multi-dimensional representation of the meanings of these words. In spaSy, the cuisine similarity is used by default, but this can be adjusted if necessary. So here I loaded the medium-sized pre-trained model and did some very quick similarity checks. So first, between the sentence, I would like to work as a data scientist, and technology jobs offered by companies like Google are very attractive to me. Here it scores a 86% similarity, which is quite high. Though you can also see in the second example, I love cats versus I hate cats. It's almost a 100% similarity. Here the model compares just how similar these sentences are in terms of what they talk about. Since both sentences are about cats, it thinks that these sentences are very similar. Next, I want to talk about rule-based matching, which is also provided by spaSy next to these statistical predictions. So why not just use regular expressions, regex? Compared to regular expressions, the matcher provided by spaSy works with the doc and token objects instead of only the strings. So it's a lot more flexible, since you can search for text, but also other lexical attributes. You can even write rules that use the model's predictions from the statistical method. So for example, you can find the word duck only if it's a verb and not a noun. So this is a common complication, that a duck can be either the animal, the noun, or to duck, a verb, used in these two types of contexts. So we need to write so-called match patterns. These are lists of dictionaries, and each dictionary describes one token. The keys are the names of the token attributes mapped to their expected values. In this first example, we are looking for two tokens with the text iPhone and X. We can also match on other token attributes. Here we are looking for two tokens whose lowercase forms equal iPhone and X. We can even write patterns using attributes predicted by the model. Here we are matching a token with the lemma buy plus a noun. The lemma is the base form, so this pattern would match phrases like buying milk or bought flowers. Operators and quantifiers let you define how often a token should be matched. They can be added using the OP key. OP can have one of four values. An exclamation mark negates the token, so it's matched 0 times. The question mark makes the token optional and matches it 0 or 1 times. A plus matches the token 1 or more times. And finally, a star matches 0 or more times. So these operators can make your patterns a lot more powerful, but they might also add more complexity. So let's see how this looks in code. To To use a pattern, we first have to import the matcher from spacy.matcher. We also load the model and create the NLP object. The matcher is initialized with this shared vocabulary nlp.vocab. The matcher.add method lets you add a pattern. Here I prepared a pattern where we look for spans that have either the base form of love as a verb plus a lowercase form of cats, and the second pattern is looking for a text vary, and we have this OP key here with the plus. Basically says that this span can occur one or more times, and we want to see this in conjunction with the text happy. Simple text, I love cats and dogs and I'm very, very happy. To match now the pattern on text, we can call the matcher on any dog. This will return the matches. And now if we look into these matches, we see that first the love cats span was identified, then the very happy, and also the very, very happy span. So this is an example of a pattern with the OP key. The phrase matcher is another helpful tool to find sequences of words in your data. It performs a keyword search on the document, but instead of only finding strings, it gives you direct access to the tokens in context. It takes stock objects as patterns and is thus more efficient and faster than the matcher. This makes it very useful for matching large word lists. Sometimes it's more efficient to match exact strings instead of writing patterns to describing individual tokens. This is especially true for finite categories of things like all countries of the world. I want to devote this last part of my presentation to spacy's pipelines, which is a very, very powerful feature. Pipelines can be understood as a series of functions applied to the doc objects. So by default, spacy does the part of speech tagging, the dependencing, parsing, and the named entity recognition, though we can also customize the entire pipeline. So after the text is tokenized and a doc object has been created, pipeline components are applied in order. Spacy supports a range of built-in components, but also lets you define your own. Custom components are executed automatically when you call the NLP object on a text. They're especially useful for adding your own custom metadata to documents and tokens. You can also use them to update built-in attributes like the named entity spans. To specify where to add a component in the pipeline, you can use the following keywords arguments. Setting last to true will add the component last in the pipeline. This is the default behavior. Setting first to true will add the component first in the pipeline right after the tokenizer. The before and after arguments lets you define the name of an existing component to add the new component before or after. Spacy does not only allow us to use the pre-trained models, but to actually train our own model. So we can actually leverage Spacy's neural network models and use it on our training data. So you could ask yourself, why should we do this? We can just rely on the pre-trained models. Well, statistical models make predictions based on the examples they were trained on. So you can usually make these models more accurate by showing examples from our use case. So you also often want to predict categories specific to your problem, so the model needs to learn about them. This is essential for text classification and also very useful for entity recognition, a little less critical for tagging and parsing. I just want to briefly illustrate how such training would work. So we would have the training data that contains the examples we want to update the model with. The text should be a sentence, paragraph, or a longer document, and for the best results, it should be similar to what the model will see at runtime. The label is what we want the model to predict. This can be a text category or an entity span and its type. The gradient is how we should change the model to reduce the current error. It's computed when we compare the predicted label to the true label. After training, we can then save it out as an updated model and use it in our application. I hope you guys enjoyed this brief introduction into spacy, into the spacy library. I think it's a pretty comprehensive library, so if you want to use some of the tools provided by the library, I would advise you to look into their documentation, which is also quite detailed. And there's a number of GitHub projects with spacy, so there's actually a lot of info online, and I think maybe even for our own projects this could be a useful tool.